The broadcast is now starting. All attendees are in listen-only mode.
Hi, good afternoon, and welcome everyone. My name is Aubrey McLaughlin. I'm the Director of Events and Professional Programs for the University of Maryland Alumni Association. We're excited you're able to join us for today's webinar, Can Privacy Exist with Machine Learning, presented by Steve Tao. This webinar is part of the Alumni Association's Professional Development webinar series, in which we hope to provide thought-provoking and valuable content that will help alumni like you achieve your personal and professional goals. We have a lot of information to cover today, but we will be taking questions throughout the duration of the webinar. Please feel free to submit any questions you have using the question box that's located in your GoToWebinar control panel. A recording from today's webinar will also be available and shared following today's session. I'd like to introduce our host for the day. Steve is the co-founder and CTO of Immuta, which is located right here in College Park. Steve has a long history of designing large-scale geotemporal analytics across the U.S. intelligence community, including some of the very first Hadoop analytics, as well as frameworks to manage complex multi-tenant data policy controls. He and his co-founders at Immuta drew on this real-world experience to build a software product to make data policy enforcement easier. Previously, Steve was the CTO at 426 Solutions, which was acquired by Computer Sciences Corporation, where he led a large big data services engineering team. Steve also holds a BS in geography from the University of Maryland. And now we'll get started. Steve, take it away.
All right, thank you for the introduction there. So as mentioned, I don't have the full hour to fill here. And I think we've got a quaint crowd here. So please feel free to jump in with questions in the questions box there as we go along. So just a quick intro about myself. Aubrey already did a great job, but I graduated University of Maryland in 1999 with a Bachelor's of Science degree in geography, and I, right out of school, spent a lot of time in the U.S. intelligence community, building analytics and software for managing data and analyzing data and managing controls on data. So that was, although I didn't do a lot of coding at University of Maryland, that was kind of where I gravitated after school. And started this company called 426, which, as mentioned, was acquired by CSC, and now we have begun this company called Immuta. So I'll spend a couple minutes here just talking about Immuta, and then we'll get to the presentation. But what Immuta does is obviously relevant to what we're talking about today. So we founded Immuta in 2015. We're about 70 people right now, and really the goal is to combine data scientists and people trying to analyze data in a single platform with the compliance and legal folks and the owners of the data. Because right now, if you can imagine, in big organizations, they are at odds with one another on how data can be used and shared across the organization. And these organizations really need to be able to leverage their data to compete with the small startup type companies that are using machine learning and doing advanced things with their data. And so typically we sell into big banks or insurance companies, but also we can sell to small companies, anyone that has highly regulated data with fine-grained controls that they need on that data. And you can see here we're a Gartner Cool Vendor in 2018 and 10 of the hottest big data startup companies of 2018 as well. So really our mission, and this ties to what we're talking about today, is to ensure the legal and ethical use of data. And so I'll start getting into the presentation here. So I'm going to come back to this quote several times during the presentation. It's from this guy named Paul Ohm. I think he teaches at Georgetown actually, and he has an article in the UCLA Law Review from 2010 about data anonymization. So if this presentation kind of piques your interest, I would highly recommend going back and reading that article, even though it's from 2010, almost 10 years old now. It still rings true and is very interesting. But he's got this quote in there that I love, which is, data can either be useful or perfectly anonymous, but never both. All right, so what I'm going to do is walk through kind of a privacy attack is a good way to think of this. And by the way, this presentation is going to kind of dive back and forth between highly technical and not technical at all, just so to make sure I can touch kind of every range of the people that potentially attended this webinar. So right now I'm going to dive into, like I mentioned, a privacy attack. So we've got here Judd Apatow and Leslie Mann. They look like they're having a really great time in a New York taxi here. But we actually can do bad things with this picture. So I can actually figure stuff out about Judd and Leslie. So just as a little background before I tell you how, the New York Taxi and Limousine Commission got something called a FOIA request about 7-8 years ago to release all their taxi pickup and drop-off data. And you can see this is like a sample row from the data, but there's millions and millions of records in here where we've got the medallion, the pickup, drop-off and drop-off, pickup and drop-off times, the pickup and drop-off latitude and longitude. And you can see that they're highly high-resolution coordinates, and the pickups and drop-offs are down to the minute. And we also get the total amount of the fare, the tip amount, and the taxi medallion. So there's obviously no personal data in here. They don't say who the driver is or who the passenger is in the car, right? But it's actually not very harmless. So if we look at this picture here, we can see that we've got the taxi medallion in the picture. We also know what time this picture was taken. It was a timestamp picture in like a tabloid website. And you can actually take that medallion and that timestamp, and we can go and find the exact taxi ride in the New York Taxi raw data. And with that taxi ride, we can also figure out that Judd and Leslie tipped the taxi driver $2.10 on a $9.60 fare. So that's not a bad tip, but there were other celebrities so basically tabloids picked up this story and ran with it and found a bunch of celebrity pictures and found some celebrities that tipped zero, but the theory was that maybe they paid cash and the taxi driver didn't actually claim the tip or something. But anyway, this is kind of an interesting story that resonates with people on what a privacy attack can mean. So this is fairly harmless, but obviously there could be more harmful things done in a similar way. So this is what we call a link attack. And so on the right here, I've got the New York Taxi data, which is that raw data that they released with millions and millions of rows. And all we really needed was this picture of Judd and Leslie with the taxi medallion at the time in order to break their privacy or do that link attack. We're able to link that picture to the data and find their individual row in that data. This is kind of a little bit of a tangent, which I'm not going to spend too much time on. The New York Taxi kind of realized that the taxi medallions might have been sensitive, and they tried to mask them, but they did it really poorly. In short, it was a hash without any salt, which probably means nothing to anyone on this call, but if you're interested in understanding how this all works, you could look up online a rainbow table attack, and it could explain why the way the New York Taxi tried to anonymize those medallions didn't really work well. But what I'm here to tell you is, even if they anonymize the medallion correctly, it still doesn't matter. So let's say that New York Taxi did anonymize that medallion appropriately. So you might say, okay, well now no one can do a link attack on this data and we're good to go. But that's actually not true, because if I knew the pickup time and the exact pickup location, you remember the times and coordinates were very specific in there, I could still use that to link to the raw data and figure out Judd and Leslie's actual trip. So maybe New York Taxi Commission says, you know what, let's make the pickup times less specific. Let's round them to like the nearest 10 minutes. So that would break that attack, but what if I knew the pickup location and the drop-off location? Well, then I'd be able to figure out how much they tipped as well. I'd be able to still find their individual row because that's unique enough in the data. All right, well, let's make the pickup locations not as specific. Well, what if I knew the drop-off location and the drop-off time? Well, let's make the drop-off locations less specific. Well, what if I hopped in the cab right after them, so I knew what time and I had their receipt? And so I could map that to the drop-off time and the amount of the fare. So you're starting to get the point here. These link attacks can really be from any source of data, as long as you have like those unique hooks in your data that you're trying to link to. So we go back to Paul Ohm's quote here. that data can either be useful or perfectly anonymous, but never both. Because if we ended up, masking all this stuff, then the data essentially becomes completely useless. Now we're protecting Judd and Leslie's privacy, but we also, like, why even bother with this data? Because no one can use it for anything useful anymore. So really, privacy is this continuum here that you see in this chart. So if you don't have any privacy up here in the upper left, then you have complete accuracy in your data. It's very useful. But if you completely anonymize your data down here in the bottom right privacy spectrum, then you can't do anything with your data. You have zero accuracy. So you really want to try to find the correct middle ground of this weighing accuracy versus privacy. And really the Achilles heel of all this is these what's called quasi-identifiers. So all those columns we were masking two slides ago with, like, the pickup location and drop-off location and pickup times, those were not personally identifiable information, right? They were just unique coordinates or unique timestamps. What made them interesting is the fact that they are quasi-identifiers. They're unique enough in the data to provide these hooks, these unique hooks to do these link attacks. We call this cardinality, when there's high uniqueness in a column. And so there's a technique that I was alluding to a little bit there called K-anonymization, which can actually make data less specific to help kind of get a little bit on that privacy curve, but while still preserving accuracy. So you can do things like chop off the end of a zip code, or round everyone's age to a less specific age, or chop off the last four digits of that coordinate, so the drop-off and pickoff is less specific. So there's problems with privacy techniques as well, like K-anonymization. So if I give this talk in front of audiences sometimes, and I do a little Q&A. Obviously, you guys can't speak on this thing, so I can't give it to you. But if you look at this, look at the last two rows there, the white males born in 1967. So if what we were worried about protecting was the problem or the ailment that the patient has, we attempted to protect that by chopping off the last two digits of the zip code and making the zip code less specific, right? And that way, someone couldn't use the zip code for a link attack, similar to how we use the medallion and the pickup time for a link attack. But the problem is, both those guys have chest pain as their ailment, right, as their problem. So we know, even though we applied K-anonymization, we still can attack this data through what's called a homogeneity attack, where we can still figure out what ailment that patient has, because what we're trying to protect is common through that group. And so, just taking that point a step further, the two pictures on the left, on the top and bottom, are before we apply K-anonymization. So we K-anonymized the coordinates in this case and made them less specific. So you see in the top picture, the two top pictures, the one on the left has the specific coordinates, and the one on the right has the rounded coordinates, or the less specific coordinates. And you really can't tell the difference between those two pictures. And that's a good thing, right? If you're doing some sort of aggregate study of, like, where the most taxi cabs are happening in New York City, you'd be able to answer that question pretty well, right? But if you look at the two bottom pictures, where on the left is the specific coordinates and on the right are the K-anonymized coordinates, you almost get like this grid-like pepperoni pizza thing going on the right, and you lose that specificity in order to protect privacy. So there is a way to get utility for these, like, non-specific questions, but protect privacy of individuals. But there's still limitations to this. Like, a very unique pickup and drop-off location could still be susceptible to a link attack, or like maybe everyone tipped the same amount at a drop-off location. In that case, we'd be susceptible to that homogeneity attack again. I just threw this in here because it makes me chuckle, and I want you guys to get the joke now. So a couple of my data scientists were at a Big Ten basketball game. Unfortunately, this isn't the Maryland game, but we've got Ohio State playing Rutgers here. And as you can see, this is like K-anonymization in the wild. They've got a single player all the way down in the player column, which is essentially a form of K-anonymization, right? No one got the joke but us. But you know that if the game actually started and as soon as one of these players scored, you'd immediately know which player is which, or at least that first player that scored, because the points would be your quasi-identifier to identify the player, right? As soon as that point column gets filled in. Okay, so just to kind of pound this point home, the what I also do when I present this to an audience is I play a little anonymization game, or the privacy versatility game. And so I took some IMDb movies and highlight some data points in them. So like the title, the year it was made, the stars. I can't believe Billy Madison's only 6.4 stars. And what we're going to try to protect is the movie title. So we'll apply these like different masking techniques and see how effective they really are. So first time I gave this talk was in the UK, so I picked this movie on purpose. And I think it's pretty easy, at least for those of us around in 1997, to figure out which movie this is simply from the description of it. I mean, heck, it says it in the description that this is the full Monty. So that simply anonymizing the movie title obviously isn't going to do you much good. This is almost equivalent to what New York Taxi did when they tried to hide the taxi medallion. So this next one's a little bit harder, right? We hid some more stuff. We did some k-anonymization on the dates. We k-anonymized the run time, so I rounded it to 3 hours. I hid the description, but just looking at the director, writer, and stars, it becomes very easy to figure out which movie this is. Of course, it's Titanic. And then in this last movie, I did a really great job anonymizing it. Like everything is covered or rounded or less specific, and no one has any freaking idea what this movie is. So we've achieved perfect privacy. But again, as you know, as our Paul Ohm quote states, that we've achieved perfect privacy, but we have no idea what to do with this data now. It's completely useless, right? And so this actually happens to be the Terminator. And if one of you guessed that, bravo, that was a really good guess. So remember what I just said, data can either be useful or perfectly anonymous, but never both. So getting a little bit into the machine learning stuff. So there's this researcher called Yves Alexander de Montoya, and he took, he's a researcher out in the UK, I forget what university exactly, but he took a bunch of supposedly anonymous credit card data. So the credit card data looked actually a lot like the taxi data if you think about it. It's like the location where the credit card swipe occurred, what they bought, how much the credit card was charged, etc. But they obviously didn't have the card number in there or who owned the card, right? So what he did was he took pictures on Instagram and Twitter that were like time-stamped or location stamped, and he only needed 3 unique data points from Twitter or Instagram to uniquely find the credit card record that belonged to that user, and he could do that 94% of the time just with 3 data points. So that's how easy it is to do this link attack on supposedly anonymized data. So you could just data is everywhere now, right? I mean, these kinds of techniques worked back in the day in the 80s and 90s at the Census Bureau because there just wasn't that much data to link it to. But now, in the world we live in, where data is everywhere, it becomes increasingly simple to do these kinds of link attacks. And so really what this boils down to is building profiles of individuals. And so it becomes very easy for these data aggregators to take data all over the place that's coming from you, either on Facebook or your phone or your Yelp reviews and anything like that, and aggregate that all together, learn about you for various reasons, probably mostly to market to you to buy something. But it's easy to build these profiles. And there's something called the GDPR, which you may have heard of, and the GDPR is worried about this and how machine learning impacts privacy in these kinds of profiling ways. So they built this regulation called the General Data Protection Regulation, the GDPR. California actually just recently released one as well that's modeled after the GDPR. It went into effect May 25th of last year. They've already fined Google a ton of money, and it actually they can fine you up to 4% of your global revenue. And so I wanted to pull it out, this one article in the GDPR law, which I'm not going to read this whole thing to you, but it applies to any EU citizen. So if you're breaking their privacy of an identifiable natural person who can be identified directly or indirectly. So I bolded indirectly. So what we actually did earlier in this slide presentation was indirectly identify Judd and Leslie Apatow, remember? So the by law, we are actually, if they're European citizens, and I know this is a complete stretch, but just to prove my point, it's very easy to indirectly identify individuals from any data that you're collecting. So really, you should consider any data you collect that originated from an EU citizen to potentially be covered under the GDPR. So, I already kind of touched on this, but there's these working parties related to GDPR where they explain kind of in more detail what these laws mean or these articles mean. And really their point is the same I made earlier on that Yves Alexander slide, which is it's super easy to make these profiles and make automated decisions based on these profiles. And they're worried about how this significantly can impact an individual's rights and freedoms. So imagine if you're applying for an auto loan and you have no idea what they're using under the covers of your data that they captured and aggregated together and used link attacks to build a profile on you to make a decision on if you should get that loan or not, and the inherent bias that might exist in making that decision. So the GDPR is really worried about this, and I would argue it's a good worry to have, and it's a good regulation to have. So as I mentioned, these regulations are coming all over the place. And people are worried about it, not just in the European Union. So there's this China Cybersecurity Law that was modeled after it. You see, I made this slide deck a while ago, but you see New York City Council debated a bill that would require the agencies to publish the source code of any algorithm they use to make decisions in an automated way. And so if you have to consider all these different regulations across the globe, and if you're a global company that has to manage your data, this becomes really, really challenging, right? I gave you a bunch of doom and gloom. If you're if you're a machine learning person and you're writing models, this sounds like bad times for you, right? But in the end, what I argue and kind of what our software does for a living is if you manage and govern these risks effectively, you can actually accelerate machine learning in your organizations. So I'm gonna switch gears here a little bit. So I've been kind of talking about why privacy is really hard to achieve and what these regulations are worried about. I'm going to change gears a little bit, and this is going to be a little bit more practical in terms of what you should be thinking about in terms of privacy if you are doing machine learning in your organization against personal data. This is where the talk gets a little bit more technical, but there are pieces of it that are not technical as well. So I'm going to run through each of these topics in detail. This is just kind of like an agenda for this next section. So a little detour here. I'm going to take us on a tangent just to make another point. So back before the turn of the century, it was really hard to take pictures of yourself. You see I've got this old camera here, and I don't know exactly how it works because I'm not that old, but you had to sit in front of it for a long time, like 20 minutes, and then eventually a picture would be taken of you. And near the turn of the century, we had this new contraption called a camera where anyone could take a picture, and it happened quickly. And you can see this quote here from Samuel Warren and Louis Brandeis, and Louis Brandeis ended up being a Supreme Court justice, where instantaneous photographs and newspaper enterprise have invaded the sacred precincts of private and domestic life. So they proposed this right to be let alone. So they were worried about these, your picture showing up in the newspaper, which obviously isn't something people are really worried about today. If your picture showed up in the newspaper, you might frame it and put it on your kitchen counter. But so kind of the way we think about this today, if you agree with me, is that you generally accept being observed. It's okay to have a camera swing on you when you're at a basketball game and have it go up on the big screen, but rarely do we accept being identified. And being identified is really the privacy attacks that we've been talking about, right? And so my colleague Andrew Burt, that's actually sitting right here behind me right now, as I give this webinar, he wrote this article, "The End of Privacy," for the New York Times, an op-ed. And again, this is something I encourage you to read if this is an interesting topic to you guys. But in summary, the rise of technology and data science has killed privacy as we know it. And really, we should stop focusing on how and when our data is collected or gathered, because that's going to happen. The toothpaste is out of the tube. You're not getting it back in. Privacy should really be about how your data is being used, and the purpose behind like what your data is being used for. And if you take that approach, then we kind of start to address some of these issues of bias models making decisions for you in a way that you don't understand or know or understand why they're happening. So this is actually, the GDPR understands this, and one of the cornerstones of the GDPR is consent. So the data, your data as a data subject, should really only be processed for either legitimate purposes that are laid out in the GDPR or things that you consented to. And there's a whole nother train of thought or discussion around like when you consent to stuff, are you really just being held over a barrel and you have to consent to it? I'm not going to get into that, but understanding if you consented to things, then that could be the driver on if your data can be used for what you consented to or not. So from an organizational perspective, not a data subject perspective, this is very different from role-based access controls. Like before the GDPR, you might say anyone that's in the group HR can see all the employee data with all their addresses and social security numbers and whatever. But maybe under the GDPR, it's a little bit more specific. We could say you need to be in HR, but in order to see the employee's address and social security number and bank account number, you need to be acting under purpose payroll or something. So it adds kind of a level of granularity that these big organizations aren't ready to deal with. That is something Immuta provides. So again, I gave this talk to kind of like a data science conference, so that's why I'm calling things out like you should start doing this. I mean, you guys on this call probably don't need to start doing this, but that's like if you're an organization that's building machine learning models, you need to start doing this. Okay, so this is actually, I'm going to get into some fun privacy engineering stuff here that I think is really cool. So really, you shouldn't be saying how much data I can get as an organization. Now, you certainly want to get as much data as possible, but the question you need to use when you're about to analyze it is how much information do I really need to do the job that I'm trying to do? And that's the way we need to start thinking about data in these organizations. So again, I'm going to take you on a little tangent here. There's this study that Uber did on all their Uber rides. So they took about 3 years worth of data on the driver information, the trip logs, the customer support data, and they analyzed all the queries against the SQL queries. So if those of you on the call don't know what a SQL query is, it's kind of like a more technical way to do a Google search on data, if you will. There's two different really kinds of queries you can do. You can do raw data queries. So if you could imagine an Excel spreadsheet, a raw data query would be like looking at the individual rows of that spreadsheet. A statistical query would be something like sum, count, or average. So like summing a column of data in your spreadsheet would be a statistical query. So you wouldn't actually see all the individual rows that make up that sum. You would just see the actual resulting sum based on the query. So the interesting result here, or the point I'm trying to make, is there's actually a lot of statistical queries versus raw data queries. You would kind of think that if someone's analyzing this Uber data, that they would probably be looking at like the individual rows, but that's really not the case. 34% of the time, they're actually just asking these aggregate questions of the data. And there's a reason I'm bringing this up, and I'll get to it. So the 34% of the Uber data science folks are using aggregate queries. So if we can assume that statistical queries matter, I can actually tell you that this is a lie to a certain extent. And how can I do that? So I've been plugging away that data can either be useful or perfectly anonymous, but never both. Paul Ohm's quote. But there's this technique called differential privacy I'm going to talk about. So to explain differential privacy, I'm going to play a game with you, and again, you guys can't answer, but just imagine you're an audience and we're doing this. So think of a number between 1 and 6. I usually tell the audience not to yell it out. You're free to yell it out if you'd like. Hold that number in your head. And now I'm going to ask you a question that you probably wouldn't want to answer in public, which is, do you hide spending from your spouse? So again, you wouldn't want to yell that out loud. But what I can then say is, I want you to raise your hand if you thought of a 3 or answered yes to the hiding spending from your spouse question. And if you imagine you're sitting in this audience with your spouse and you raised your hand and your husband or wife turned to you, you could say, hey, honey, I was just thinking of a 3, right? So you can actually preserve privacy through plausible deniability through this technique. But I also can understand the percentage of people that actually hide spending from their spouse because I understand the probability of you selecting a 3. So I can kind of bang out those statistics and come up with the real answer to my statistical study, right? So if you think about differential privacy, it's adding noise to the responses so that all the responses aren't true, but it's a level of noise that allows you to still come to valid conclusions, at least at a high level. But this is obviously only limited to statistical queries. So again, remember we said that our statistical queries matter. So you can only do differential privacy on statistical level queries. You can't ask kind of row by row questions with differential privacy. You'll see this quote down here from this guy, Frank McSherry. He's one of the original academics that worked on differential privacy. He actually just posted a blog 2 days ago on this same blog thread, I think, where you guys should go read it. It's spectacular, but he basically compared differential privacy to contraceptives, where you have 2 consenting parties that want to do something. You guys use your imagination, and the contraceptive allows them to do that in a protected way. So if you think about privacy and machine learning, it's kind of a similar concept, right? You have your data as a data subject, and you in turn are expecting your privacy to be respected to some respect, but you're still expecting some sort of benefit from that from the service provider that's using your data. So, like going back to the Uber example, you're letting Uber know where you're getting picked up in the interest of being delivered to somewhere else that you need to go. But you might be given other benefits that they use differential privacy to protect your privacy to do other studies against you. So I just thought it was like a really fun and interesting analogy to describe this. So I encourage you to look at that. So I kind of already touched on this, but you can only ask aggregate questions of the data. There's actually a couple other catches here. So if you ask the same question enough times, you can actually beat down what is the real answer and figure it out through statistics. And there's a technique called privacy budget to avoid this. I'll talk a little bit more about this. And it can also be really hard to figure out how sensitive of a question you really ask to determine how much noise to add. So just going back to the privacy budget thing. So let's say we were trying to protect the rating instead of the movie name, because again, we're limited to aggregate questions. So if we added noise to the average rating, when someone said, give me the average rating when the movie is the Terminator, the real rating was 8. So the first time we give a noisy response at 7.3, the next time we get an 8.6, then an 8.3, then a 7.6. And just after these 4 answers, we start to narrow down what like the real average rating is for the Terminator. So you can actually set budgets on how many questions users can ask in differential privacy, but you can also, we have a technique in Immuta where we basically cache the response. So we'll give you the same noisy response for if you're asking same or similar questions of the Immuta platform. So we can actually apply differential privacy on the fly. And again, so I'm getting into some technical mumbo jumbo here. I hope it's useful for some folks on the call. But just the way this actually works is a query will come through Immuta, and this is like how. So the point of the slide is, how could New York Taxi have done it? So instead of releasing their raw data with the taxi medallion masked, they could have instead released it through differential privacy and allowed interactive queries against that data with noise injected, and then that attack would have been impossible, yet the data still would have been useful going back to our Paul Ohm quote. So what we could do is, when that query comes through, instead of just querying the raw data, we'll query 4 samples of the data, and those samples contain, imagine an equal kind of contribution of the distribution of that data. And so if that query is pretty broad, like give me the hottest location for taxi pickups at 6 o'clock every day, that's a pretty broad question. So all these samples will probably return a very similar answer. And so we know that that's not a sensitive question. We shouldn't add a lot of noise. So we give a very non-noisy answer back to the person asking the question. But if I asked that like question about where Judd and Leslie Apatow, like if I said, give me the average tip amount where the drop-off location is this specific location and this specific time, obviously only one of the samples is going to respond with an answer. The rest of them are going to be like, sorry, I don't have an answer for that. And that way we know there's a lot of sensitivity associated with that question, and thus we apply a lot of noise and you don't know the real amount that they tipped. So that's kind of how it works under the covers. So that's differential privacy. I'm going to talk about another attack that I think is like kind of crazy, and it leads to another differential privacy technique that you can use for protecting your machine learning models. So there's this public model out there, machine learning model. It's only limited to a certain set of people, but you can basically throw any picture of the person at it, and it'll tell you who it thinks that person is. So let's pretend this person is Bob here in this picture. And I have a picture of Bob. I'll throw Bob at the machine learning model. The machine learning model will say, hey, there's an 83% chance this is Bob. There's a 70% chance it's Sally, and there's a 20% chance it's Ralph, whatever. And so what these researchers did, Fredrickson, they wrote this paper on model inversion attacks. And so basically they were able to extract training data. And what they did is they kind of, let's say you knew someone's name, but you didn't know what they looked like. That was basically what they were trying to figure out. So like do the opposite. So let's say we knew Bob's name, but we wanted to figure out what Bob looked like. So what they did was they threw like 1,000 really fuzzy pictures at this model, and they figured out which fuzzy picture got the highest score for Bob. And then they took that fuzzy picture and made it a little bit more refined, 1,000 different ways, and threw it back at the model. And they did that over and over again and kept grabbing the one that looked more and more like Bob. And they were able to create this picture on the left that looks a lot like Bob does on the right? So they were actually able to generate a picture of Bob just by pinging this model and asking questions of it, of like what it thought looked like Bob or not. So kind of quite crazy. This is called a model inversion attack. There's all kinds of different model inversion attacks you can do, but you can actually build your machine learning models in a way that avoids these inversion attacks by adding noise in your model. So there's this technique called Patt, which is created by Nicholas Paperno and Ian Goodfellow. I actually think this has been since turned into, if you've ever heard of TensorFlow, which is what's the right word for it? Not a platform, but a framework for building machine learning models. There's an implementation of Patt and TensorFlow now. But the idea is, I mean, if you look at this picture, it looks a hell of a lot like this picture, right? So what they do is they build a model 4 different ways in this example, and based on the model's decision on if it's healthy or the user has cancer, in this case they're determining who has cancer or not taxi stuff, but the if the models are all in agreement, we don't have to add a lot of noise. But if they disagree, then we would add some noise to that response. And so if you train your model this way, you actually protect from this kind of inversion attack. Like no one would be able to throw fuzzy pictures and figure out what Bob looks like at this model. This is just some more details on that. All right, so what the heck is the point of all I was just talking about there? So we've covered a lot here. We talked about risks to privacy and how they can be attacked, including that model inversion attack. We've talked about privacy techniques like K-anonymization and differential privacy and their limitations. And so again, you have to get to this privacy versus utility trade-off. So really, the goal should be you should protect your data subjects' data always. So you really don't want to have these data free-for-alls where everyone can see everything about your data subjects in your organization. You can do this through things like purpose restrictions, which I talked about. Remember the camera example. And privacy is really about how your data is being used, not what's being collected. And you can mix that with techniques like differential privacy or anonymization. All those things combined really helps your organization do its machine learning in a trustful way, in a way that your data subjects or your customers can trust you. And so you owe it to your customers and yourself. You don't want to be Zuckerberg in front of Congress. And you'll notice that organizations are starting to use this to drive sales. I don't know how many of you have seen the recent iPhone commercial, but iPhone is about trust and your privacy. And so Apple is really pushing this. I mean, frankly, they're doing it because their biggest competitor is all about collecting all your data, Google. But that is, the angle that they're taking. And I'm going to skim through this part because I want to make sure I leave time for questions at the end. But this is more related to like an organization that's actually doing machine learning. But again, I'll ask a couple questions about, how many of you actually have models trained on data, and do you actually know what data is going into those models? And usually there's no hands raised in the crowd, which is sad. And so there's this regulation that was created called 11-7, which is really directed towards financial institutions, but the guidelines in it are very useful for any organization building machine learning models. And they really try to identify two major risks, which are errors. So this is like input in the model itself and the outputs, and then misusing models. So like if you built a model for one purpose and then try to use it for another, that's a bad thing. But I'm pointing this out because really what we've been talking about, about what we were talking about today, is not only just about privacy, but is tightly coupled to how you should be managing your machine learning risk in general. And that's kind of what I meant by, like, if you have these controls in place, you actually make the development and use of machine learning models in your organization better and faster. So things like, are you accurately representing your users? So again, like the data subjects and using them appropriately, the relevance of them. Of using that data, and do you really need, what information do you need to get your job done, and are you using appropriate and legal proxies, the ethical use of that data? And then if there are changes in policies about what you're able to see in your user or your data subject data, how do you enforce those controls and audit that? And of course there's obviously model level controls and output level controls, which I'm not going to talk about. This is really about visibility into what's going on and avoiding these errors or misuse with your data subject data. Okay, so this is, I think, the last slide, just to recap. So really, don't use your customer data beyond the scope of what they expect. Understand and capture consent when possible, and then have these controls in place to enforce purpose-based access rather than just kind of free-for-all access. And then, are you only using the data necessary to make decisions? So you're going to have to make decisions about this utility versus anonymization trade-off, and think about using differential privacy in your organization. And then the bookkeeping around what data is going into which models, and understanding that visibility I talked about in the last slide. There's also another great paper written by the Google folks, Hidden Technical Debt in Machine Learning Systems, and change anything changes everything. So machine learning can be a house of cards. If you change one little card at the bottom, the whole thing can come crashing down. And a lot of this is about that bookkeeping and understanding what data is where, and enforcing these controls in the right places, so that you have that control and auditability. Yeah, so I'll stop there. I appreciate the folks, the alumni that was able to join. Here's my contact information if you're interested in hearing more, and I'll turn it back over to Aubrey to close things up.
Great. Thank you, Steve. We'll go ahead and take some time for questions now. As a reminder, if you do have a question, you have a question box that's located in the Go To Control panel. Please feel free to type that in. We'll give just a couple of minutes here for any of those thoughts or ideas. Steve, I did have a couple of questions for you. We talked a lot about different types of attacks. What is the most frequent type of attack or the most common piece of information that tends to be given out or breached in terms of privacy?
Yeah, so the it's most commonly those link attacks, just because people have, there's a lot of examples out there. Like Netflix did a challenge where they released a bunch of movie reviews and hid the movie reviewer, and basically someone took that and linked it to IMDb reviews. And we're able to like figure out who the reviewers were, and someone sued them, and it was a big mess. But again, it's just like anything. So that's kind of the question you posed is actually the problem in itself. You don't know. It could be anything highly unique in the data that someone could use to link to. So there's not, I think that's like the challenge, right? Is that you don't know what someone could use, the universe of possibilities someone could come up with to find a little hook in the data to hook some other data to break your privacy. I'm sure New York Taxi wasn't thinking about a celebrity photo in a cab when they released that New York Taxi data, and being able to use the coordinates of that photo and the timestamp of that photo to break celebrity privacy. So it's just like, you kind of don't know. And one thing you can do is just by knowing how unique the values in that column are, being cognizant of that and understanding that the more unique the values in those columns are, the higher likelihood it could be used for a link attack against your data.
Great, thank you. So I saw in one of your later slides the mentioning of Mark Zuckerberg with Facebook and everything. So can you talk a little bit about the difference between maybe a data breach and something like Facebook, where we're willingly giving our information out and then it's being maybe sold without us really even knowing? Can you talk a little bit about the difference and then how that differs in terms of just the outcomes?
Yeah, so that's a great point that I wasn't really touching on in this, which is, well, there's kind of two things you brought up there. So there's data breaches. So there's really two separate concepts, and I could do a whole talk on this too. But we're seeing this convergence of security and privacy. So security is really the things that the chief information security officers have been worried about in organizations forever, which is like, I don't want someone to hack into my database and steal all my customer data, right? And we see this all the time. These breaches happen all the time. Poor University of Maryland had a breach, right? So this is about keeping the bad guys out and the good guys in, right? Or allowing the good guys in. And privacy is a step further to that. It's a gray area with that privacy versus utility trade-off, where like the good guys are still seeing the data, but you only want them to see enough to do their job so that you're respecting the privacy and the rights of your data subjects. So that actually is now becoming a big concern in these big organizations. So it's not only about security, but security and privacy are converging into the same problem. But to your point, Facebook just, I don't know if I remember all the details exactly, but they just had an API that basically that company took advantage of to break the privacy of the individuals in Facebook. So the fact that Facebook had that API was, bad on them, but really it was like the company that leveraged that opening to then do their bidding with all that customer data. So, companies need to be really careful about what they put out there in terms of how they make their data subject data accessible. And this goes back to the don't worry about how your data is collecting, but worry about how your data is being used stuff, right? So if I guess the root of the issue is that if Facebook would have been more respectful about how they shared data, or if they actually could capture consent to do what they were doing, which I think technically they kind of did, then there wouldn't be an issue there. The problem is consent. I mentioned this earlier, is a whole nother can of worms, because if you buy your new phone and this window pops up and says, hey, if you want to use this phone you just spent $800 on, you need to consent to X, Y, and Z, like they've got you over a barrel, right? So there's other challenges associated with that that I think need to be addressed in society going forward, but that's kind of out of scope with the privacy piece.
Great, thank you. Yeah, I remember a couple of years ago, there was I think there was a shooting on the West Coast, and there were some text messages that Apple wouldn't release for a really long time, just given the privacy. And I remember like how much of a uproar that really caused, just in terms of protecting privacy of somebody when you could have figured out, I guess, the root of the issue. But that's a really great point.
Yeah, I hadn't heard that one.
Yeah.
But yeah, I might want to dig into that. Yeah, so I mean, again, that's, Apple's taken this hard stance on that, which honestly I think is a good move. It's going to earn trust with their customers and drive business for them. I would argue that trust is going to be a big component of consumers making decisions on what they're going to buy.
Are there companies or organizations that come to mind, I mean, aside from Apple, that maybe are doing a really great job at protecting their customers and that data privacy? Or are there industries that come to mind that maybe are more susceptible to, and maybe it's a lot harder to control that privacy?
Well, the organizations that are doing a good job of it are, of course, the Immuta customers, right? But mostly it's I would say there's a big spectrum. The people on the head of that spectrum are the folks that have been dealing with these kinds of controls for a while now. So these are like healthcare and finance, because they've had to deal with HIPAA or all the rules around financial regulations. The folks that are going to struggle with this are the ones that this is all new to them, and kind of GDPR is getting thrown in their lap. So everyone but those ones I just mentioned. I guess I could throw insurance in the group of people that have been dealing with this for a while now too. And so I kind of joke, like, my background is the U.S. intelligence community. I joke that the U.S. intelligence community has been dealing with this problem forever, and now it's just becoming a problem in the commercial world that people have to deal with, and that was basically the thesis of why we started Immuta.
That's awesome. We have one more question that came in. Do you think that companies should be held to greater levels of transparency? So like giving customers access to their data or letting them know how algorithms are calculated, or are there trade-offs to a greater degree of transparency?
Yeah, so there's a lot of things we could talk about there. So the GDPR actually requires this, so I didn't get into it, but one of the GDPR requirements is that you must be able to explain how your model's making a decision. And there's some argument around what that really means. My take on that is that you don't need to actually explain the fine-grained nitty-gritty details, but you at least need to explain to the user like what the model is trying to predict, what data went into it from you as a personal data consumer to make that decision. And so I think there is some obligation as an organization to do that, especially when you're making critical decisions. Like if you're making a decision if someone should get a mortgage loan or not, you should be able to explain to them why they didn't get the mortgage so they can come back to you in a month and have a better looking application, right? If you just say to them, sorry, you can't get the mortgage because our algorithm said so, and then the consumer's like, well, then how do I get a mortgage? And you say, I don't know, I can't explain that to you. So there's a trade-off there. Again, everything's all about trade-offs where no one really cares how Netflix decided what movie to recommend you. I mean, that could be a completely black box model, right? You don't care to know how that works, but if something is telling you if you can get a mortgage loan or not, you're going to care to know how that works. So there's transparency at the model level, and then there's transparency and at the data level, which is how your data is being used. And I absolutely think there needs to be controls around that, and that's really what the GDPR is getting at, so that these data aggregators can't just go around sucking data from everybody and building these user profiles without anybody knowing it. And essentially what they can do is build those profiles and then sell those profiles to other people to make decisions on mortgage loans or what ad to send you or whatever it may be. So that's really what they're trying to put a stop to. And like I said, California built a very similar law to the GDPR that is now, I can't remember if it's in effect or about to go into effect, but and there's more coming. Other states are talking about it, and there's actually proposals for federal regulation related to that as well.
Great, thank you. It looks like we've covered all of our questions. Just to let everybody know, we will be sending a follow-up email from today's session that will include the recording of today, along with Steve's information. So please feel free to contact Steve directly if you'd like more information or to discuss your own personal situation. I want to just thank everyone for joining us today, and I want to thank Steve for hosting today's webinar. Have a wonderful day, and go Terps. Thanks for joining. Bye.
Thanks, see ya.